now. Hi, everyone. Welcome to week 4 of Techquitable Futures. Today, we'll be going over the topics of strength and linked lists. And it will be presented by myself, Wentao, and Zach Chauvin. And Zach, since this is first time you're presenting with us this cohort, would you like to introduce yourself?
For sure. Yeah, so good morning or good afternoon, everyone. Nice to meet you all. My name's Zach. I'm a software engineer working at a startup in San Francisco called Middesk. Before that, I was at Facebook for a couple of years, but I've been involved with Techquitable for a couple cohorts now. Yeah, I really like the program, and I love to chat about this sort of stuff and do interview prep and chat with people as they're starting their careers in tech. So yeah, I'm psyched to be here today. Today, we're talking about two really important topics for interviews and for programming more generally, strings and linked lists. These are both data structures that come up all the time in interview questions. And so we'll walk through some of the definitions as well as a couple example problems. And definitely feel free to use the chat or just jump in whenever you have questions. So I'll kick it off first with some definitions around strings. So a string is a pretty common data structure used in programming languages. You can think of it as a special kind of array where each of the elements in the array are characters. So, so in this example, my string is the word weighty. And so in some languages, for instance, a language like C, you wouldn't just have the characters. So here we have an element in the array for each of the characters, W, E, I, all the way to Y. But in a certain language like C, you might also have what we call the null terminator, which is essentially a null pointer that indicates the end of the string. So that way the system, basically when you're printing out a string, the system knows to print all the way from the W to the Y and stop at this null terminator. But in most languages that you'll be using, if you're using JavaScript or Python, those languages are memory managed for you. And so this concept of a null pointer doesn't come up. In that case, a string is really just a series of characters. And there's certain operations that you can do on it. For instance, here, this is Python syntax. And if we were to take a slice from characters 1 to 6, then we would get these characters from the E to the T. And so that's an example of an operation that you might actually do on a string. So the motivation, why learn about strings? As I mentioned, these are pretty often asked in algorithm and data structure questions. And it's important to become familiar with the techniques associated with string problems because they do come up so often. And lastly, it's important to, even though there are kind of like arrays under the hood, it's important to treat strings as separate from arrays because there's particular operations that we do on arrays that don't necessarily make as much sense in the case of a general array. Probably the most common from this list would be joining. So as an example, let's say that you have a bunch of different strings for each of the words in a sentence. Something you might do is join all of those strings on a space character, which would essentially build a new string out of all of the individual strings. And so, yeah, you could compare strings, you can split them, you can replace parts of the strings, you can find substrings within those strings. All of these are different methods that you should become familiar with as they could come up in interviews. Any questions about strings so far? Things making sense? Great, we can keep moving on. So strings on themselves, there isn't too much that we have to go over in terms of base content. And so we'll actually just jump right into an example problem. And palindrome is probably one of the most common string questions that you'll see. The definition of a palindrome is a string that reads the same when it's reversed. So for instance, pop is a palindrome. It reads forward POP. It also reads POP backwards. Radar, race car, detartrated, which until this morning when I was prepping, I didn't know was a real word, but it is a real word. It means to take tartrates out of something, commonly wine. And then this last one, yeah, you can also have whole sentences that are palindromic. For instance, drab as a fool, aloof as a bard. And so the problem is going to be to implement a function that checks whether the given string is a palindrome. So we're going to pass in a string. It's going to go through our function, and we're going to return a bool, either true or false, to indicate whether or not it's palindromic. So this is, as part of the program, we're trying to get more familiar and more comfortable with turning problems into algorithms. And so does anyone have any ideas as to how we might go about this problem? And it's okay if they're not fully formed.
I have an idea.
Yeah, what are you thinking?
Why don't we take the string? I'm speaking in terms of JavaScript. Take the string, split it into an array. Take the array, sort it in this descending order, and then check whether or not the characters there match. So that's one way we can do it.
And so you would be sorting all the letters, and what would the sort order be?
Ideally alphabetically, so like from A to Z. I just want to check that I have all the words,
Interesting. So like maybe like if there's an even number of all of the letters, then that means that they're kind of appearing in a palindromic way.
Right.
So for instance, like with pop, we'd end up with 2 P's. So like, yeah, so sorting it would kind of allow us to have an account of the different characters. So for instance, radar, we'd have 2 R's, 2 A's. One challenge that I might have with that though is that I think that you could have the right number of letters, but that they would be not necessarily in the right order in the original string. For instance, what if we had RA, AD, R? In that instance, it looks like we have the right kind of combination of letters, although in the original string, they're not ordered in the way that makes the original string a palindrome. Does that make sense?
Yeah, I see what you're saying. That makes total sense.
Yeah, because I think I was tempted originally to do something like counting or sorting, but I think a challenge with those is that you lose context about where the original letters occurred in the string.
And it looks like we have another hand raised from Darren.
Yeah, Darren, what are you thinking?
I'm thinking we can create a left pointer that points to the beginning of the string and a right pointer that points to the last character of the string. And inside a loop, while the left pointer is less than the right pointer, we compare, we see if the character that the left pointer is pointing to is equal to the character that the right pointer is pointing to. If they are equal, we can keep comparing. If not, that means that there's a mismatch. There's a lot of palindromes, so we can break. So then we can like return false, and that means it's not a palindrome. Oh, and if they are matched, then we just advance. Then we just like increase the left pointer by 1 and decrease the right pointer by 1 to move on to the next one.
Yeah, I think that's definitely sounding good. It's kind of comparable to how a human might do it, and that a human might just kind of look at the first and the last and work their way in. And so that approach is making a lot of sense. In terms of writing it out, like kind of as a strategy before we look at the code, I think Darren put it really well in terms of having, Darren was mentioning the use of pointers. And so that's kind of one solution where you actually have pointer references to the beginning and the end. Another very similar way of doing it is where you're just keeping track of what indices you're looking at. So you would be starting at the 0th index and then the last index and kind of working your way in. But the structure is the same in that If they don't match, you can return false. If they do, you can keep working your way towards the center. In terms of code, so this is the one that's using indices rather than pointers. So we start at 0 and then length -1. This is an important thing to remember in when we're working with arrays or with strings. The last element is at n-1, where n is the length of the array. For instance, if we have a 3-character string like pop, the largest element is 2, because we have 0, 1, and 2. And then while the left is less than the right, we're going to compare. If they're not the same letter, then we're going to return false. Otherwise, we can walk in by increasing the left and decreasing the right. If we get all the way to the case where left either ends up being the same as right, because we're right in the middle, then we can end up returning true. And does anyone want to take a stab at why this has linear or O of n time complexity?
Well, in this case, we're just iterating through the array of characters once. Yeah, so it'll always be linear.
Exactly. Yeah, this while loop will execute at most n times or kind of n over 2 times. And each time that it iterates, it's doing a constant operation. And so constant operations. And so overall, it's O of n, just like you said, Valerie. Thanks for that. And then the space is constant because we're not using any additional space other than the original string. So this is kind of our first crack at it. This will work great for palindromes like pop and radar, but does anyone see any kind of shortcomings with this approach? Are there any palindromes that this wouldn't work so well for?
Yeah, so if we have any letters which are in uppercase and lowercase, they will have different values, like stored as different values. And also if there's spaces within, like if it's a sentence, then there'll be spaces, so it won't apply.
Exactly. Yeah, thanks, Valerie. And so as an example, this drab is a fool, loop is a bard. Here as appears as a single word, but in the reverse, as has the space in the middle. And so our original algorithm would fail to actually show that that is a palindrome. For those that are more visual, this is a pretty cool resource that you can check out that actually visualizes some of these algorithms. And so it essentially walks through the code and shows what it would look like in terms of memory. So that is a good resource to check out. And then similar to what Darren had originally said, this is kind of describing the same algorithm, but with the use of pointers. And so having that left pointer at the beginning of the right pointer, but otherwise the algorithm works in a fairly similar way where we're walking those pointers in towards the middle. But to return to what Valerie had pointed out about some kind of trickier cases where maybe you have upper cases, maybe you have non-alphanumeric letters or characters, we need a little bit more, we need to modify our algorithm slightly. For instance, for a man, a plan, a canal, Panama, a classic palindrome, how is it that we might do this? We might tell whether or not it's a palindrome, knowing that there might be some of these corner cases. Does anyone have any ideas about how we can modify our algorithm for this case?
You could lowercase all the characters that you come across.
Mm-hmm. So when we're doing the comparison, essentially do like a comparison of the two lowercase. I like that for sure. And then how about the spaces and the commas, the non-alpha numeric letters or characters?
I was thinking like one could either trim it out, or you could also just skip it if it happens to be a space, like if it's not an alphabetical character, then you could just skip it and not compare.
Mhm. Exactly. Yeah, I think those are the two approaches that I was thinking of. One where you kind of pre-process the string to take out any of the non-alphanumeric characters, and even in that step, you could lowercase as well, and then you just pass it through the original algorithm. In terms of time and space complexity, that wouldn't affect your time complexity because that's doing a single pass and we already have a linear solution. But what would that do to the space complexity? Let's say we like built a new string that was that kind of trimmed version.
I guess it will make it ON because you're creating another, well, in Java, you can't really, like strings are immutable. So you'll have to create another variable just specifically to match that, I guess. Yeah.
Yeah, exactly. If you're not doing it in place, and you're working in a language where your strings are immutable, you're going to end up with a space complexity of linear. And so that's why here we kind of dive into that other solution that Valerie was mentioning, which is around kind of on the fly skipping characters that that we don't need to consider that are non-alphanumeric. So let's have a look at what that looks like. So same as the strategy in the first, but with extra checks for alphanumeric values and handling this, yeah, kind of stating what we were talking about. In terms of code, it starts off pretty similar. We have a left and a right that store the indices of what we're looking at. But we have these inner loops that essentially, while we're looking at letters that are non-alphanumeric, while not the character at the left index is alphanumeric, we can keep on walking forward. So keep pushing that left. And note that just because we're walking the left in doesn't mean we have to walk the right in this instance, because we're just walking the left in order to skip a non-alphanumeric character. And so we'll actually keep the right where it is. We'll do the same for the right. And we have these extra checks to make sure that we don't accidentally walk into a case where now left is the same as right or greater. And then from there, it's just the same as our original. Compare the two strings. But then I think it was Fariha who had said, sorry if I'm mispronouncing your name, who had said to lowercase both the letters and then compare. If they're not the same, we'll return false. Otherwise, keep walking in. And so we managed to keep constant space and we still have linear, but now we have something that can handle non-alphanumeric characters. Any questions about, yep, go for it, Wenta.
Oh, just to kind of throw a question for everyone. We see that the time complexity here is O(n), but when we look at the code itself, like there's like a nested while loop. So we might think, hey, because like there's nested while loop, shouldn't this be like O(n) square? But wanted to kind of get your explanation on why this could still run O(n) time.
Yeah, does anyone have any ideas why even though we have this while inside, can we make an argument that this is still linear? Oh, then.
Because you're not going through the entire, because you're not, I guess, because you're not going through like the entire string and then inside the internal while loop, you're I guess only looking at that character, a few characters, or maybe if you're only looking at that character to see if it's alphanumeric. I'm not sure. mm, I'm not sure that explains it sufficiently.
It's definitely on the right track though, because normally when we see these n-squared things, you're right that it often will be looking at the whole string or a big chunk of the string. In this case, I would say an argument for why we're going to stay linear is that these inner while loops also help us to kind of eat into more of the string. And so anytime that these while loops are executing, we're going to keep on walking towards the middle of the string and we're never going to go back. And so even though we have nested while loops, each of these characters will only be considered once, because with each iteration of any of the while loops, we are walking toward the center. How's that fitting for people?
Makes sense.
Yep, and
Cool.
just one more note to add is this like calls for like alphanumerical check. This is also run in O1 time. It may not seem obvious from this like code, but a lot of languages have a kind of like a built-in check or this kind of check imported from like a standard library. And you could imagine kind of like implementing this check against like some kind of like a hard-coded set of values that you had to check for alphanumeric, or even getting like the ASCII numbers of these like letters, right? So you can see that some like basically letters, if they're like alphabet or numbers, they will kind of like stay within like a certain range of this like ASCII numbers. ASCII numbers are basically kind of like this like integers numbers that computers like represent these like letters in. So they can do that quick check, and which could be done in 001 or constant time. So this call itself to check that is very fast.
Cool. That's all I had for palindrome. If there aren't any more questions, then we can probably move on.
Sounds good. Well, thanks, Zach. I'm going to just share my screen from here.
I had a question. If we're moving, before we move on to linked lists,
For sure.
I often see questions about minimum or maximum subarrays within a string, or even similar questions that come with arrays. And I was wondering if we would get like any guidance on how to solve such problems.
Yeah, I think those are, I would have to brush up on that, but I think that those are fairly like standard algorithm questions. And so it's kind of a good example of a string problem. What we probably could do is grab one of those from LeetCode or something, and then put it in the Slack, and maybe chat through any questions that people have about the solutions for those.
Yep. Valerie, I can be on point to find similar questions and post it on Slack and facilitate some discussion and practice around that.
Okay, sounds good. Thank you.
All right, any other questions? If not, we'll move on to linked list. All right. Let me just set up a chat over here. All right, so let's start talking about linked lists here. So we already learned this kind of like other data structure of arrays. And just as a quick review, arrays is this contiguous block of memory with fixed size. So this allows us to have like a quick access to any element given a certain index. But on the other hand, linked lists are different because they take bits of memory from here and there, connect them together, and they're dynamically sized. So this kind of property offers us like different advantages at different times. So and we'll kind of get into that in a moment. But here's a basic definition. So each element or node contains two components. The first component is data, basically any kind of data that's supposed to represent the value at that node. And this could be like integer, string, could be like a JSON blob, or any kind of value or data type. So that's the first component. And the second component is that it also has a pointer or reference that is pointing at the next element. And then one thing is that the one exception here is that the last element in linked list doesn't point to anything, because just naturally linked list just ends there. So, and then the only thing you need to also remember to keep a linked list is to also remember where the first element is. So you also need to have like a helper like variable or data to kind of like point to where the first element is. So in this example here, first of all, in terms of implementing a node, if you were to use a kind of a class, you can kind of implement it this way. So this is just using like a Python language, but you can imagine this also getting implemented in like the language of your choice. But you would have like things like a data and next pass into initialization. So then you could keep track of those two components of node that we talked about. And so you kind of mentioned, we also need to remember what the first element is. So in this kind of example implementation, we'll have another class called linked list that only has head. And this head would be essentially be pointing at the first node in this linked list. And linked lists also have various methods that you would need to kind of like to like implement and use. And these operations are head or tail, previous and next, linked, search, insert, and delete. So we'll also quickly go over what those operations are, but once again, it's important that you know how to work with these operations and as well as like how to implement them. And just heads up, don't try to memorize these right now, but it would be nice to also just go over in your free time to just try to get more kind of like more of these details brushed up on it. So first, let's start with like next operation. And what this does is that it basically says, given a node, to show me the next element. In Python, the language kind of passes the object around by reference. So it is kind of like as easy as just passing in a node element and calling the dot next attribute. And if you want to get the value, which is different from next node, right? Because the next will be kind of pointing at the node itself, which would have the data as well as the pointer to the its next element. Next value would just be only kind of getting back the data component. So to do that, you also need to do the node.next, but then specify that you also want to get the data. So you also kind of specify the data attribute here. And all this operation is done in one time. And now moving on to the tail operation, what this says is that given the head node of a linked list, show me the last node. So you could imagine that now in order to get to the last element from the first element that you have access to, we need to iterate through like all the elements in the linked list in order to get to the last one, which is the tail. So here, what we have is that given a head node, we can kind of like keep like reference that as like a current. And while basically current exists and there's like a next element you can visit, we will basically kind of update this like current variable into the next element or next node each time. And when this break condition, when this while condition kind of like is no longer satisfied, that means that there's like no more next element that you can reach to, or the fact that you have arrived at the end or the tail. So you just return that current node at the end. And this operation, because you have to kind of iterate through each element in linked list, it will run in O of n time, or it's linear. And then now moving on to the operational lengths, given the head node of a linked list, give me its lengths. This is also running O of n, and this is because it's also very similar to finding the tail, because now this is basically now you're calculating how many elements or nodes are in this linked list. So you basically have to kind of pretty much do the similar thing as like what you did with tail, but now keep a counter. Here we have called it as like length, and basically increment each time you see a new node in this linked list, and then you just want to return that length at the end. Now moving on to a more interesting one. This is the search operation, and this asks, does a given value exist in a linked list with the given head node? Going to take a pause here, but does anyone have ideas about how you may want to implement this?
You would start with head and then go through each node and check the data of each node and compare it to the value that you're looking for until you get to that the node that you want and then stop there.
Yep.
And
Yeah.
return that.
Yep. And you have exactly the right idea. And any ideas about why this will also run in O(n)?
Because you're visiting, you're just like visiting like n nodes until you get to the end of the linked list or find what you're looking for.
Right. So once again, the big O runtime kind of like suggests like the runtime in the worst case scenario. So in this case, the worst case is that the value that we're looking for is located at the very tail end of the linked list, or the fact that the value didn't even exist, which it would have like required to iterate to like every single element in this linked list, right? So that would be the worst case that we will have. So that is why we will have O(n) runtime here. But as Faliha mentioned, this is exactly how we implement it, because basically kind of like iterate through each element and check whether that value of that node is equal to the value that we're looking for. And if there's a match, we just return true. Or you may want to just return that value. Otherwise, you would just return false, or any kind of false z value. Moving on. Now we have an operation that says we want to insert at head. So we basically want to kind of update whatever head element that we have, and this could be done in one time. So here, what we do is we can just essentially create a new node with this new value, and now the next pointer or the next reference is going to be pointing at the current linked list head. And this is a little tricky, but because now we want this new node to be the new head, then we have to kind of go back to the linked list, which is the pointer that's supposed to be pointing at the beginning of the linked list, to point back at this new node that you just created. So this is interesting that we can do in one time, and it's much faster than, for example, inserting a new element in the beginning of the array. And that is because if you were to insert a new value at the beginning of the array, then you basically need to kind of copy over like all the values that were existing, to follow this like new value they just inserted. And this copying operation is gonna take like O(n) time. However, here, because like linked list is like dynamically pieced together, and you have like this access to the head, you can actually do this in one time. So there's a little bit of difference that you start to see with regards to runtime between linked list and array because of the different properties that they have. And then moving on to the delete operation, we want to delete the first appearance of the given value from the given linked list. This is essentially a mix kind of built on the idea of this like search element, because first you need to find where that first value appears in linked list, right? So essentially, first you're writing kind of like some code that is very similar to the search operation, but then just like delete. Well, and then once you find that value that you're looking for, this delete operation requires you to do an extra thing, which is that once you find that node, what you want to do is basically this is like all written within this kind of like conditional here. But if there's a previous node, you want to update the previous pointer of next to be pointing at the current to the node that's being pointed by the current dot next. So this part is essentially saying that, well, there's a previous element or node. Please like update the element, the reference from the previous node to the next node, so that essentially skips over the current node that we're trying to delete. Otherwise, if there's no previous node, that means that we actually found this matching node at the head. So now what we want to do is we want to update the linked list dot head to be pointing at the current dot next, or the node that exists at current dot next. Does that make sense for everyone? So this is essentially, how we are kind of like updating the pointers to make sure that the node that we want to delete is getting skipped over, right? So this is what we do if we find the value that is like matching the value that we're looking for. Otherwise, we'll have to kind of like move on to the next element in this link list. In which case you have to make sure that, obviously you want to keep track of the previous. So you have to set previous and equal to current. And now your current will be basically be pointed at by current.next. So similar to the search operation once again, but the difference, as I explained, is in this conditional statement where you want to kind of like update the pointers of the previous nodes to skip over this current node that you're trying to delete. And you also want to make sure that you keep the previous node around so that you can also access their values. All right, so now that I have explained all the basic operations and definition of linked lists, we'd like to move on to doubling linked lists, which will be, once again, be presented by Zach.
For sure. So yeah, we chatted through singly linked lists, but doubly linked lists are kind of a modified version of this, where not only do you have the data and then the pointer to the next node, but you also have a pointer. Each node knows what the previous node is as well. And so in this example, 3 knows that it points to 1, but 1 also knows that it points to 3, and that 3 is the previous node. And then Wen-Tao went over how with a singly linked list, the last node is going to have a null pointer because it has no next. The analog to that in a doubly linked list is that the head or the first node has a null pointer in its previous because the first node has no previous. Cool, next slide. What this looks like in a Python class is just the same as a single linked list where we have data and next, but we also have a third attribute, which is going to store a pointer to the previous. And so that's what this third class attribute is. Cool. And then why would we do this? Why wouldn't we just use single linked lists? This can make it a little bit easier to reason about insertions or removals. So Wen-Tao went over the code for the removal, and it involves like having a local variable which is always keeping track of the previous. If you have a doubly linked list and you're looking at an element in the middle of your list that you want to remove, it's actually a little bit simpler to remove it because you have references to both the previous and the next node already in that thing that you want to remove. And so by just doing a little bit of shifting around those pointers, you're able to remove or insert a new element. So that's one reason. The other reason, which might actually be more compelling, is that you're able to traverse the list in both directions. So that's a little bit of a funky thing about a single linked list, is that because you only have forward pointers, you really can only traverse from front to back. With a doubly linked list, let's say for some reason you got to the middle, but now you want to be able to go backwards, or you want to start at the end and move towards the front. All of that is possible because each node knows what its previous is. So yeah, these are 2 reasons that you might see questions about doubly linked lists, or if you're thinking about using a linked list in order to solve a problem, but you think that these 2 things might be helpful, you might think about using a doubly linked list. Cool. Okay, so we actually have 2 different questions for linked lists because they are a little bit more of they can be tricky to wrap your head around. And actually, Wen-Tao, do you mind if I share for this just so I can make sure I can reference all the?
Yep, take it over.
Great. I think you have to stop first.
Oh, okay.
Perfect. Thank you. Okay, so we're going to jump into this second question. Perfect. Are you guys seeing this in full screen?
Yep.
Great. Okay, so we're reversing a linked list. So let's go over the problem statement first. So like normal, we're going to have a pointer to the head of the list, and we're wondering how do we reverse it. So in this instance, the input is 1, 2, 3, 4, 5. So 5 element linked list that is singly linked, and we want to output the reverse of that 5, 4, 3, 2, 1. Where now 1 is the tail, it's pointing to null. So this, this is a pretty canonical linked list question. I'm wondering if anyone has any ideas about how we might go about this, even if they're just kind of tidbits of the solution. Any ideas?
Is this a singly or doubly linked list?
It's singly linked list. Yeah, so that's always a good thing to ask your interviewer. And for instance, in this instance, we haven't specified. So yeah, it's singly linked.
I'm gonna have an idea.
Yeah, what are you thinking?
I think we start at the head. We save the reference to next in a temporary variable. We say that the head next is null, because the old head is going to be the new tail. And then you repeat the process. So then you go to the temporary next, and temporary next that the previous is going to be the head. The old head, and you repeat the process until you hit the last node. And at the end, what you're gonna have is the old head is not gonna be the tail, and the old tail is not gonna, it's gonna be the new head.
Mm-hmm. Yeah, that's definitely making sense to me. And how do you pronounce your name?
Dario.
Dario. Okay. Yeah, so Dario is definitely on the right track. He's explaining a kind of iterative approach where we work through this one at a time. And he kind of keyed into a key part about modifying linked lists, which is that you have to be really careful about when you set the next to something else. For instance, looking at this one node, if we set its next to be something else, for instance, maybe we set it to be null because we want it to be the new tail. If we haven't first saved what its next is in a temporary value, we're going to lose the rest of the list. That's like kind of a funny thing about linked lists, is that you can accidentally lose the rest of the data structure if you're not careful about what you're setting the next of a particular node to. So yeah, I definitely like that idea. There's two different solutions. One of them is recursive and one of them is iterative. Because Dario is kind of hinted us in the iterative direction, let's actually start with that one. And so what we're going to do, which is pretty similar to what Dario was laying out, is that we're going to have something that stores the previous, something that stores the current, and then something that stores the next. And we can iterate throughout the entire list, but as we're going, we're going to want to make sure that we store that next in a local variable. Only then are we able to reverse that kind of chunk of the list by setting the currents next to the previous. And then we can kind of walk forward. So looking at this in terms of a GIF, we can, I'm not going to attempt to keep up with this because it actually goes pretty quick, but I'll let you guys watch this for a sec just to kind of start to get a feeling for what this looks like. We'll wait for it to restart too. Okay, so it's about to restart. So we have this 3-element linked list, and we're gonna store pointing to the next, and only then can we reverse. And then we move both the previous and the current forward, and we keep going. Remember the next, reverse, and then move them both forward. And in that way, we kind of just go throughout the entire thing. And at the end, once the current has gone all the way to the end where it's null, the only thing left to do is make it so that the head points at the previous, because the previous, if we've gone through this entire process, is now the last element. Looking at this in terms of code, it's actually not too much code, but it's pretty dense. And so we start the previous to be none. We start the current to be the first node. And then we're going to walk through our linked list while the current isn't none. Again, really important, we store the current next in a local variable called next. That means that now that we've stored it away, we can actually do the reversal, which means the current's next is going to be the previous. And note that the first time that we do this, previous is none. So sort of like Daria was saying, we want the old head to become the new tail. And so that works out well, because now the old heads next is going to be none, which is exactly what we want. We want the old head to become the new tail with a next of none. Once we've reversed, we can kind of walk forward by pushing forward the previous and the current, and then we'll repeat, continuously storing the next temporarily, and then reversing that next to print the previous. At the end of the day, all we have to do is set the linked list head to be what the last previous was, because the previous ends up pointing at the old tail, which is going to be the new head. So that is the recursive solution. It has a time complexity of n, like many of these linked list things do, because we're just iterating a single time over the list. And then it's going to have a constant space complexity, because we are only storing a couple pointers. We're not storing anything that's proportional to the length of the list. Cool. Now that we've looked at the iterative, let's actually think a little bit about the recursive. Sometimes when you're trying to come up with a recursive solution, it's helpful to think about, how would I solve this if I had a function that was able to reverse a list? So for instance, let's say that I knew how to reverse 2 through 5. Does anyone know, if we had a function that could reverse 2 through 5, how we would construct the entire reversed list?
Can you please repeat that?
Yeah, for sure. There's kind of lots in there. So we're looking for essentially like a recursive statement about how we're going to reverse this list. And in order to make a recursive statement, we can pretend like we already know how to reverse shorter lists. So let's pretend that we already know how to reverse 2 through 5. And so we could call this function on 2 through 5, and we'll get back a list that's 5 through 2. If we've done that, then what's kind of the last couple steps that we need to do in order to get the entire reverse list, now that we have 5 through 2, and we've got this one node as well?
Can I give it a try?
Yeah, for sure.
So we know that our recursive function sending is returning a node. So we could do 2, you said 2, right? So we know we got from 5 to 2.
Right.
So we could say 2.next is equals to the recursive return value of the previous call, I think.
That's kind of on the right track, that we're going to use the results of the recursive call, and we need to set 2 next to something, because right now it's nothing. Right now it's the end of a, because we just have 5 through 2, so 2's next is pointing to null. And so we're going to set 2's next to be this node that was kind of alone. To look at this, to visualize this a little bit, first in words, what this is going to be is we're going to divide the list into 2 parts, the first node and the rest of the list, kind of like we were talking about the 1 and the 2 through 5. We can call the function reverse for the rest of the linked list. So that's where the recursive call is, and that's where you kind of pretend that you already know how to reverse a shorter list. Then we're going to do the part that Daria was talking about, where we link the rest to the first. And then lastly, we'll just fix the head pointer, and we'll see what that means in an example. So here we've divided the first and the rest. So we have a pointer to the first node, and then we have a pointer to kind of the second and everything else. Then we're going to call the reverse function. And so now we have this list that's 4, 3, 2. And the last step is that we need to remove this link and create a link from node 2 to 1. So that ends up looking like this. And then, and the cool part is that we can actually do this, even though we don't have a reference to the end of this linked list, we can do it pretty easily because we do have a pointer directly from 1 to 2. And so in order to reverse that pointer, we're going to just say the first next, that next is going to be first as well. It's a little mind bending. So first is 1, first next is 2, and we want 2's next to be this 1 node. So first next is first. And then since this is going to be the new tail, we say that first next is null, and then we're good to go. So we have essentially reversed that last pointer. And lastly, we're just going to say that the new head of this entire linked list is going to be rest, because rest is what we got back from reversing the rest. All of that is pretty hypothetical until we look into the code. So let's give it a shot looking at the code. Whenever we have a recursive solution, we need to have a base case. So in this case, the base case is if we ever get to the case where head is none or head's next is none, then we just want to return the head, because the reversal of an empty linked list or the reversal of a linked list that only has one element is itself. That's normally how a base case comes up, is that you get to such a small instance of the problem that it's trivial to solve. So here we have our base case. We're going to reverse the rest of the list, which is this is where the magic happens. We're calling ourselves. So the rest of the list is just head.next. And then we're going to do that step where we point the end of rest to the old head. And so head.next.next, we're doing this step right here where we reverse this arrow. And so, and then we make the, this head is now the tail. And so its next pointer is going to become none. And then the cool thing is that because this function is supposed to return a pointer to the new head, to do that, we just return rest, because rest is the head of this reversed final part of the list. So that's a little bit of a mouthful. Recursive solutions are always like a surprisingly small amount of code for a complicated solution. Does anyone have any questions or anything that I can clarify about this recursive solution? I'd encourage you to kind of, if this is still a little tricky, gaining comfortability with recursion just comes with looking at lots of these and kind of internalizing them. So I would definitely encourage you to come back to this one and look at the diagrams and kind of convince yourself of the validity of this solution.
Could you explain?
Yep.
The head.next equals head again?
For sure. Yep. So that is the step here where we now have the, like, this is almost correct because we were able to reverse 2 through 4, but we have to do this last thing where we make the, right now it's 1 is pointing to 2, but we want it to be that 2 points to 1. How we do that is that, remember that because 1 is currently pointing to 2, we can say, if we want a reference to 2, we say first.next. So this is first.next. And we're going to set the next on first.next to be this 1 node. So in code, we're saying, here's first.next. And we want to set first.next next to be this 1 node. How's that?
Okay, I see. That makes sense.
Cool.
It was
Yeah, the next is definitely a little gnarly, but it's kind of, you can think about this as like second next is going to be the first. First next is really second. Second next is equal to first.
Right, it was the 2 that's equal to first.next. Like once you said that, that kind of made it clear for me.
Sweet, good.
Thank you.
Okay, any questions before we move on to the last interview question? Great. Let's do it.
Cool. Thanks, Zach. Yeah, as Zach mentioned, working with recursion can be kind of like mind-bending. And this is also like a first time as a cohort coming across recursion. So definitely kind of encourage everyone to like, look carefully closer and try to follow the code. You also probably get like more intuition as you kind of implement the code yourself and see how the values change over time. And then one more note is that Techquitable will also have a section, session dedicated for recursion coming up. So hopefully you get more practice through that session. And so yeah, so just a heads up on recursions. And now let me just present the last in a kind of like a sample question to you guys. Okay, can you guys all see the screen?
Yes.
Alrighty. Yep, so this sample question is about removing linked list elements. So yeah, you may be wondering how's that different from like a delete operation that we previously went over. It's slightly modified, and here what we want to do is remove all elements from a linked list that have the specified values.
And Mentao, we're seeing we're not seeing the presentation right now. We're seeing
okay.
a different slide.
Sorry, wrong screen.
There you go.
Perfect. Okay. Yep. So yeah, just once again, the difference is that we now want to remove all elements that have the same, like that has a matching value instead of just like a single value. So for example, like we have a sample linked list here that goes from like value 1, 2, 3, 4, 5, 6, and we want to remove the value 3 from here. In this case, it's very simple, and there was only a single element that matches the target value of 3. So what we do is then, as we went over, we want to basically update the next pointer coming out of 2 to be pointing at this node's like next, which is this like node with the value of 4. But this is just one example case, right? Kind of want to make just kind of open it up to everyone and ask what are different kind of cases that you may run into with like different types of inputs. So curious to hear if anyone has thoughts.
I think if we try to remove the 6, we might have an issue.
Okay, so Dario, you kind of mentioned this example or this case of like removing elements from the tail end, right? Because the 6 value is the tail end here. And when you say that we might have an issue, what kind of issue do you foresee?
So what I thought you did in the first, when you removed 3, was you went to 2 and you said 2 that next is equals to 3 that next. That's what I thought you did there. But if you try to do that for 6 doesn't have an next, so you're going to have an issue there. Got
it. Yeah, that's a good point. But yeah, that is like one case that we need to handle, and we'll later dig into how we can do that. So yeah, so that's one good kind of type of case that we could run into. And kind of curious to hear, are there any other cases that we could run into?
We could run into a case where the value we're moving is at the head. In that case, it would need to be we need to make sure that we're able to update the head since there's no previous node to like do the next thing with.
Yep, Darren, you also brought up a good point, which is like a case that's like kind of the opposite of what Dario suggested, which is, well, what happens if we have values that we want to remove from head? And right, so in that case, as Darren, you mentioned, we'll have to kind of update where the head is pointing at. So for example, like let's say that we have to remove 1 in this case. The head is supposed to be kind of like pointing to 1, but if we have to move it, then we have to know to update the head to point at 2. And that could also be like not just single values, but like multiple values, right? Like if we have like a slightly different like linked list, and let's say we have like multiple ones laying at the top, like located around head, then we'll have to kind of like delete multiple of those like values at the head, and then get to the new head. So yep, so that's another good case to handle for. Kind of curious to hear if there are like any other ones. I don't think we have heard from Gabby, Elmish, or Jung today, and want to always go for like 100% participation. So, do you guys have any thoughts on any other cases that we may run into?
Could there be duplicates?
Yep. So duplicates could be like another thing to that we have to handle for, right? Yeah, just having an assumption that, yep, it's basically there will be multiple values that we'll have to like delete in a row, and that could be like basically like located right next to each other, or it could be kind of spread out from each other, right? All right, so yeah, I mean, you guys kind of like all brought up good cases here, so I'm, I have just kind of listed like the 5 major cases that we could think about here. So case number 1 is the case in which the linked list is empty. With any kind of problem, we always want to check for any kind of like invalid input or like empty input. So we may want to have like a handling around that. I'm gonna like just focus on case 4 and 5 at the moment. Case 4 and 5 are the cases that Dario and Darren have raised. So case 4 is when the head nodes have a target value, right? So if that were the case, like let's say in this example, like the XX is the values that we want to delete. So we need to make sure to delete those 2 values at the head and make sure to point the head to the new head at with this value of 3. And similarly, if the last node has the target value that we want to delete, then Dario kind of mentioned that, yeah, we might run into trouble because there's no next like element here. So we would need to kind of like have like some clever way to make sure that, yeah, we can just delete the last element and just end the linked list with this value of 5. And we'll kind of get into that. And then the 2 other cases that we can also run into here is case number 2 is when all the nodes have a target value. So in which case we want to make sure that we delete them all. And in the end, it would just kind of have like an empty linked list. And that's like case number 3 is, is what could be like when middle nodes have the target values. In which case you want to make sure that you want to update the next pointer from the previous node that doesn't have that to the next node that also doesn't have the target value. So then you skip over those nodes with target values, right? So those are like all the cases. And as Elmish had mentioned, it's also fair to assume that there could be multiple values of these things. All right, so let's think about how to handle each of these possible cases. So case number 1, when the linked list is empty, how do you want to handle that? Well, this is a pretty simple one, which is, yeah, we just want to check for like an empty linked list and return immediately if that was the case, because this will kind of save us from running any kind of invalid operations on this empty thing. In case number 2, well, what do we do if all the nodes have the target values? This one's also pretty straightforward, which is that all the elements should be removed to return an empty linked list. And moving on to case number 3, this is the one in which the middle nodes have the target value. And here we have like 2 different approaches that we can use. So approach number 1 is what we call the look ahead approach. And this is basically saying that, well, from current node, we want to check the next node's value. And if the next node's value is a target value, then we want to skip to the next, basically next node, like basically like, sorry, this is also a little confusing to say it, but it's like the next node is like next pointer, right? So in code, that would be represented as like current dot next. So to kind of go along with the visual, what this is saying is, so here we want to be deleting those nodes with like these XX value, right? So it was saying that basically by the time you get to this like node with the value of 2, we want to basically see if this like next node that's being pointed by this node has that value that we want to delete. And if that was the case, then we want to update this basically arrow current.next to current.next, which is basically kind of skipping over, right? But in this case, yet again, this value, this like new node that we have updated to also has the X that we want to delete. So we also need to kind of handle or like, detect that this is also indeed a node that we want to delete, and even kind of proceed with this update of this pointer. So you might want to do current.next again, so that this pointer would eventually skip over those nodes and be pointing at this node with value of 5. So this is what we kind of called like the look ahead approach. There's also another approach, which we call the keep previous node approach. So here, what we could do is we could keep the previous node as temporary variable, right? And if the current node has a target value, then you want to set the previous node's next pointer to the next node. This is basically essentially the same thing, but kind of like looking from like a different angle. So here you'll be like basically saying that, yeah, by the time you get to like this node of X, you realize that this has the value that we want to delete. So what we want to do is have the previous node, which basically will be a node of 2, to be pointing at the next, the current's next. So we'll be pointing to this one, right? So there are two approaches that we can do here. Either way works. It's more like a matter of preference at this point. And moving on to case number 4, which is the case that Darren has raised, which is how do we handle the case in which the head nodes have target values? Here we can handle it by updating the head to point at next node until next node does not have the target value, right? So this is also pretty straightforward. And then lastly, what do we do if the last nodes have the target value that we want to delete? Here we just want to just set the next pointer of the last node with non-target value. So in this case, it will be a node with value of 4 to null or none. So once again, to kind of summarize all those 5 possible cases that we just ran through. One, we can just always check for empty linked list. And the second point is that we also want to remove all head nodes with target value in the beginning. And afterward, the last point is afterward, we want to loop over all the nodes, and if the node has a target value, remove it by removing the next point, by moving the next pointer to point at the next node. And otherwise, you want to keep moving along the list. So this is kind of proposed solution number 1. This is basically saying that while basically head is not none, so here we're just kind of checking for an empty linked list here. So and if there's also a case in which the head dot value is equal to this value that we want to delete. So this is the case that Darren raised, which is when those nodes that we want to delete are located at the head. What we want to do here is then we want to basically have the head point to the head's next, right? And this operation of updating the head is wrapped in this while loop, because there could be multiple nodes that we want to delete that's located around head. So this is basically going to keep deleting until this condition breaks, which is finally the head is no longer had the value that we want to delete, or basically head becomes none, which means that we, essentially all the elements, all the values in that linked list was the values that we want to delete. So this is basically it's this 2 lines here may look a little simple, but it's actually doing a lot of things. One is checking for empty linked list. And the second thing that it's doing is that it's also deleting any kind of values that we want to delete at the head. But once we get out of that, we can start to address all the other cases, which is, so now, then we can kind of introduce this new variable called current, and we want to set current to equal to this new head that we are returning. And here on, what we are saying is that while current is not none, basically this also allows us to check that we are also operating any kind of like operation against like a valid node. And then once again, there are also a bunch of conditional statements here, but if current.next is not done, this is saying that if next node is basically like non-empty and current.next.value, so basically the value at the next node is equal to this value that we want to delete, then what we want to do is we want to update this next pointer from the current value, a current like node, to point at current.next, which is the nodes that are like 2 places away, right? So once again, this is kind of like updating, the pointers, because we have detected that the next value has the value that we want to delete. Otherwise, we can just kind of keep moving along the list, and it would just update current equal to current.next. So then the current will be pointing at the new, will be pointing at the next node. And basically, this is kind of like doing this like look ahead approach that I have mentioned. And after we run this code, then we can finally return the head that's basically pointing at the beginning of this linked list, or this modified linked list. So that's kind of like the one approach to do it. Another approach that I would like to introduce to you guys that could simplify that solution a little better is just kind of like a helper data structure that people call Sentinel or dummy node. So if you look at the previous solution, once again, it actually requires to provide a special handling for the case when the head nodes have the target values. Basically, this is the first 2 lines here, right? We wanted to check for the case in which the values, the nodes at the head have the values that we want to delete. So that's why we had to introduce those 2 lines to basically add like a special handling for that case. But what dummy node or sentinel nodes could do is that it can basically help us generalize the situation and say, well, what if we can just like, basically use a generic solution? The generic solution, as that I'm referencing, is like, basically the rest of the solution here. Basically generalize this to also handle the case that's being handled by the first 2 lines here. And to do that, the Sentinel or dummy node can help us do it, because what this is basically like a dummy or like a fake node that has like whatever like random value, right? But you kind of introduce this as a new head, and by doing so, you now kind of like make the original head to be like this kind of middle node, right? And because like now like the original head is like part of this like middle node or this like modified linked list that has a dummy head, you can basically apply the solution that you had to handle the middle case, the cases in which the target element is located as like middle nodes across this entire thing. So go through like a code example. Here we're kind of introducing the dummy node with this like, with instantiating this like list node with whatever value. So, but here we just kind of like assign a value of 0 here. And we're saying that, okay, this dummy has next, please point this to the head that we originally had. And now this part of the solution is pretty much exactly the same as what we had here. It's basically the solution to kind of handle like the rest of the cases, which is basically while current.nodes next is not equal to none, because we want to be also applying the look ahead approach here. What we do is, once again, check that if the value at the next node is equal to the value that we want to delete, then we update the pointers to point at the current nodes like next, or basically the nodes that are 2 positions away. Otherwise, we want to move along the list and set current node to be current node.next. But instead of returning the dummy head, because dummy head doesn't really mean anything, we want to actually return the original head. So to do that, what we do is we just return dummy heads.next, which should be pointing at the original head, or this like new head that you should be returning. So yeah, so this is kind of like a trick to kind of like help us generalize the situation and simplify the code. But both solutions kind of work equally as nice and would handle this problem for us. So yeah, so this kind of wraps up this like interview problem. And before we kind of wrap up for today, just wanted to take a pause here to see if you have any questions about this problem or anything that we have covered today in today's presentation.
I had a question.
Yep.
When Tao, in that last solution, so we went over a couple different cases, and one of the cases was the case where a couple elements at the end are the target. Could you talk through why this actually does handle that still?
Got it. So yeah, so Zach's question kind of like references to the question that Dario kind of raised in the beginning, which is basically case number 5, right? Like when the last nodes have the target values, how does this kind of generic solution gets applied or handled as well? And basically, this is if you kind of look at this like main chunk of the code, basically it will get handled because you're always looking ahead, right? You're always looking ahead and trying to see if the next node's value actually has this like value that we want to delete. And if that's the case, then we want to update the next pointer to point at that like node that we want to delete next pointer. So it's like it becomes like the current dot next, right? So this is kind of like happening here, where this like if statement here on line number 7, this is the step that we're looking ahead and saying, okay, is the current node's dot next dot value, which can be rephrased as the value at the next node is equal to this value that we want to delete. And if that was the case, then current nodes dot next. So now we want to update the current nodes like next pointer to be pointing at current nodes next dot next, which is saying the next node's next pointer. In the last case in which those like target values are located at the end, if it's like a tail end, then this next, if this let's say if the current nodes dot next is like actually pointing at the tail node, then tail nodes next should be pointing at null, right? So that was the case. The current dot next would now be pointing at null, and it will kind of like nicely break out of this while loop because to get to that end, while current node dot next is going to be none at one point, and it's going to be basically kind of break out its while condition, and move on to the line where we just return the solution.
Makes sense.
Yep. So Zach, thanks for asking for that question. But Dario or anyone else, does that explanation like makes more sense to you?
Yeah, I'm just struggling to see why or how you cover when you have like, let's say, like 3 values that are the same. Like look at the text that I sent the message. Like I don't see how that works for that case.
You don't see. Okay, so basically, when there are multiple values that you want to delete, is that right?
Yeah. So you got the last value is 4, but you got 3 of those.
Right. So yeah. So let's kind of go through that example. So let's say, okay. So in this case, we want to remove 4, right? So then at one point, your current node will get to the point where you're pointing at this node with value of 3, right? That's why we kind of like start to like do all this kind of like update or like all the magic happen. So now once you at this like node with 3, and you basically check whether the current node what the value at current node dot next is pointing at. The first time you do it, you realize that okay, the next nodes is going to have a value of 4. So then what I want to do is just update, right? So update just like current nodes dot next into current nodes next. So now this like next pointer that's coming out of 3 is no longer going to be pointing at the first 4. It's going to be pointing at the second 4, right? Because we lined the code at line 8, which is where we update this like next pointer. But also notice that we're also not updating the current node here yet, right? So now we're basically doing this check again, which is saying that okay, what is the value at this like next pointer that's still coming out of 3, right? Now it's pointing at basically the second 4, but because this like second 4's value is like still 4, which is the value they want to delete, we basically kind of go through the same thing again, right? So now we will basically now updating the next pointer that's coming out of 3, that was like now pointing at the second 4, and saying that okay, now we want to update this pointer to point at the next node that's coming out of this like second node of 4, so which is like this like final and third and final node of 4, right? So we're basically doing that update again.
I get it. That makes so much sense.
Because this isn't the while loop, and the only time in which we are moving along to the next this like current node is basically when we are sure that the next value is not equal to this value that we want to delete, right? So this is kind of captured in this like else statement, but that's like when we want to like move the current node to like the actual next. But otherwise, we'll actually keep deleting because we're kind of stuck in this like case where the next node actually has the value that we want to delete. And even have like multiple like values that show up. We just keep deleting thanks to the thanks to the code on line 7 and 8, and because of the fact that this is like wrapped in this while loop. Does that make more sense?
Yeah, that works. And so you take into account where, like we're looking at the last 4. The last 4 doesn't have a next, right? So you could say 4 that next, and that still works.
Yep. I mean, because let's say by the time you get to this like that basically the tail node, right? And tail node also happens to be the node that you want to delete. The tail node by definition should be pointing, the tail node's next pointer should be pointing at like null, right? So when you update that, the current node will eventually have current node's next pointer should be pointing at null at one point. In which case you should be kind of stop running your code, and that kind of code, that kind of check is done by this kind of like condition in the while loop, right? Because I think the case that you're worrying about is if you call next on null, that's going to be an invalid operation, right?
Yeah, I see what you're saying.
Yeah. So because like we're also detecting when we should be stopped doing all these kind of check inside this condition within this like while in this like while statement, we're kind of prevented from ever reaching that invalid operation state. Yeah, but yeah, that's a good question. Any other questions that you guys have for this question, or any other topics that we went over today? All right. If not, I understand today's lesson went pretty long, but just wanted to kind of highlight a few other resources. So if you would like to kind of get more comfortable with linked lists or practice on more problems, these are the links that we recommend checking out. And then there's also one more anime question that we didn't really have the time to go over today. So this is why we have an appendix. But there's also another question around detecting a loop within linked lists. That's also pretty interesting to check out. It may seem hard, but once you know the trick, it's actually fairly easy and fun to solve. So yeah, I recommend checking it out on your free time. And otherwise, I believe we're out of time. So yeah, so thank you guys so much for joining us today. And Zach, thank you also for joining us for today and presenting this lesson to the class.
My pleasure. Thanks for all your time. I was really impressed today with the participation. It's awesome to have everyone jumping in and helping out with the problem. So thanks for being engaged.
All right, thanks everyone. And I hope you guys have a nice rest of the weekend.
Thank you. You too.
Thank you.
You too. Thanks, guys.
See you.